In Part 6, we'll look at recommended practices and design examples for heat pump systems. Our learning outcomes for Part 6 are to understand recommended practices for cold climate air source heat pump design and to apply our learning to home design examples.
Welcome to Part 6. Part 6, recommended practices and design examples. This is a process flow diagram showing the typical steps that should be taken in the installation of a heat pump. The steps are first determining the customer's preferences and needs, and then looking at the current heating system and the layout of the home. After that, then a load calculation must be performed for the whole house or alternatively for zones of the house. Based upon that, then the sizing is determined for the heat pump, how big it is in terms of its capacity. And then the optimal system design, which loads are going to be served, whether it's going to be ductless or ducted, and where to locate the equipment. Then, as far as controls are concerned, if there is a backup heating or supplemental heating, they have to be integrated with the heat pump system. And then the controls are set up and the set points are determined, and the installation is performed in accordance with manufacturer's specifications. And then lastly, the system is tested and commissioned. These are the recommended practices for load calculations and for system sizing selection. They are to conduct a takeoff and then do the load calculations without adding any safety factors, because we know that the safety factors are already included in Manual J. And then want to be sure that the actual conditions are reflected in the load calculation. And lastly, to use the specified indoor and outdoor design conditions for that particular geographic location. On the right are the sizing and selection considerations. First, you want to use the NEEP database that lists cold climate air source heat pumps as well as different manufacturers' data. And then you want to ensure that the outdoor and indoor units are identified as compatible with the Air Conditioning, Heating, and Refrigeration Institute database. In other words, your outdoor unit, and there are different options for the indoor unit, but those two must be paired and identified within the AHRA database as being compatible. And then to determine whether you're going to displace part of the load or whether you're going to replace it in full, whether you're going to retain perhaps the legacy system and use it as a supplemental or backup heat, or if the entire house is going to be heated with the heat pump. And then each zone should be looked at the maximum design condition. And for mini splits, the recommendation really is to never exceed 3 indoor heads per compressor. The next recommended practices are for locating the indoor heating element or air handler, and also in the case of where you have a ducted system, the recommended practices for ducting. On the left are the recommendations for the placement of the indoor air handler. Place them usually in the top third of the wall for standard heads, but not to be any closer to the ceiling than 6 inches. And wherever possible, place the air handler where it can have a maximum amount of distance or clearance from the front of the head to the rest of the room. And this will help to mix the air within that room. And then it should be located as close as possible to the middle of the room and not in the corners of the room. And then lastly, consider the need to deliver heat to each room. For ducting systems on the right, ensure that the ducts are adequately sized in accordance with Manual D, and specify that the ducts should be sealed at all junctures and in crawl spaces and attics or the garage. And they should also be insulated. Design the new ducts to minimize friction losses And there you want to use large radius elbows and turning vanes. And lastly, you should avoid specifying new ducts outside of conditioned space wherever possible. Okay, these are recommended practices for locating the outside unit and considerations certainly for the condensate that will be generated from the heat pump, which is going to be outside. For the outside unit on the left here, we're looking at selecting locations for the outside unit where there's enough free airflow. And at the same time, we want to minimize the refrigerant line lengths. And in order to accommodate snowfall, risers should be specified. And then we want to specify locations not to be under or near a window or close to a neighbor's window. Also, we want to avoid an installation where there's a unit above where condensate could drip on another outside unit. For the condensate system, on the right are recommendations for the field installation of the condensate drainage system. These are recommended practices for the installation of the condensate system. First, the system should drain by gravity, if possible, and therefore the piping should be sloped in a downward fashion. And the termination or point where the condensate piping ends and the condensate flows out should be well away from any walkway or crawl space. Specify an external condensate pump if it's needed. And in that case, since it's in a cold climate, it'll have to be protected in some way from the cold. And then ensure that the condensate will drain without being blocked by frozen condensate. This is an example of a single-story home with a relatively simple layout. The current heating system is a single-zone radiant baseboard heat using a boiler, and the home is poorly insulated and poorly air sealed. A potential design solution is pictured with the heat pump's heat shadowed in orange. Most of the heat is going to the living room, but some spills into the rest of the home, which could potentially satisfy the whole house load on very mild days. In this case, the legacy system will be controlled by its own thermostat, which is relocated, and be used to heat the bedrooms, bathroom, and kitchen. A second head, or perhaps an additional mini split, could potentially be added to the master bedroom. This slide shows the same house as shown in the previous example, but this house has an existing ducted forced draft system. In this design solution, the ducted natural gas furnace is completely replaced by the heat pump, and a portion of the existing ducts are reworked to incorporate a centrally located air handler with resealed and insulated ducts. The furnace is removed and no backup system is installed. This is an example of a typical two-story, three-bedroom home. In this example, the current heating is an intact hydronic radiant baseboard system fired with oil. The homeowners are first cost sensitive, but they do want to reduce their carbon footprint. The home is modestly insulated and air sealed. An example design solution could be heating the downstairs with the ductless heat pump, the area shown in yellow, and using the existing legacy system to heat the upstairs, shown in red. The existing hydronic radiant baseboard system downstairs could be retained to provide complete backup heat for the entire home. This example shows the same house as the previous slide, but with an existing forced air ducted system. The current heating is an old forced air system with poorly maintained ducts. The master bedroom is frequently cold and physically isolated from the rest of the house, and the homeowner is first cost focused and cannot currently afford a full house system. In this solution design, the downstairs and isolated bedroom, shown with the yellow shading, are heated with a multi-split or alternatively two mini-split units. The existing heating system is kept and used to heat the other two bedrooms shown with the red shading, and for complete backup for the entire house. These are examples of some common design failures. Oversizing the system, where sometimes contractors may use rules of thumb derived from previous systems that they're more familiar with that are fired with gas or oil. And in this case, if it's oversized, then the heat pumps will short cycle during mild temperatures, and that will hurt the overall energy performance or efficiency. The backup system, if that continues to provide most of the heating, it's not providing the design intent. And this can result from poorly integrated control schemes, or the homeowner may not be informed adequately on how to operate the system, and it can lead to the backup heating doing most of the work. The idea that one solution fits all, thinking in those kinds of terms, many contractors can get comfortable with a specific type of system, maybe a two-head ductless multi-split, and they attempt to apply that to all solutions. And that is a common source of design failure. And then suboptimal indoor head location. Location, as we talked about, is important for the indoor air handlers. And some contractors may not be as familiar with point source heating and systems and the air mixing that's involved. If the indoor heads are placed where they're blocked or they're too close to the ceiling, they'll be unable to provide adequate heat for a closed door bedroom or office. Some of the lessons to be learned are that variable capacity heat pumps operate differently than traditional heating systems, and so they need a different design approach. Load calculations are critical for the proper sizing of the heat pump, and even more so than in the case of a traditional heating system. And the sizing does affect comfort, performance, efficiency, and durability of the system. Design decisions and integration with supplemental heat require careful consideration and the home's layout and homeowners' needs. And then finally, the control schemes must consider integration with backup or supplemental heat if it's not a complete replacement system.
In part 6, we learned about the recommended practices for cold climate air source heat pump design, including understanding the customer's preferences and their current system, and performing accurate load calculations, as well as determining an optimal system design. We applied what we learned to some example home designs, keeping in mind that we want a right-sized system suited to the specific needs of each home and homeowner.